Welcome to today's webinar, The Power of Collaboration, Validating CONVERGE for Offshore Wind Turbine Modeling in the OC6 project, brought to you by Convergent Science. Thank you for joining us today for the second event of the new 2025 CONVERGE webinar series. My name is Matthias Sulis and I am part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and hear from my colleague Shengbai Shi about the work that was done as a part of the OC6 project. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our client. Now it is time to introduce our speakers for today's event, Shengbai Shi. Shengbai is a principal research engineer at Convergent Science. He obtained a master's degree in mechanical engineering from Johns Hopkins University in 2012 and his PhD in ocean engineering from the University of Delaware in 2016. Since joining Convergent Science in 2016, Shengbai has worked on development, validation, and support for wind energy and other renewable energy projects. Without any further delay, I will now pass the ball to Shengbai. Thank you all.
Thank you, Mattia, and thank you everyone for attending this webinar. And I'm very happy to be here to share our experience in the OC6 project. And I also want to thank our collaborators from the University of Florence and the University of Massachusetts Amherst. Without their efforts, this presentation or this webinar won't be possible. Let's talk about the background of the OC projects first. Well, actually, this OC series was organized by the International Energy Agency, trying to verify or validate the current numerical modeling tools for the applications of the offshore wind turbines, especially for the floating offshore wind turbines. Because due to the complexity of the physics involved in this applications, people were not sure if our current numerical tools will be capable of doing the simulations for this kind of problems. Therefore, IEA set up a series of efforts targeting on different aspects of the applications, trying to see whether or not the tools will be capable or what kind of developments are necessary for the future works. And the OC6 stands for the Offshore Code Comparison Collaboration Continued with Correlation and Uncertainty. And this is a continuation of the previous OC projects. And it's part of the IEA's Task 30 program. You can find the details of the introduction of this program on the IEA's website. For example, in this figure, you can see that the OC6 project consists of 4 different phases. The phase 1 is for the nonlinear hydrodynamics. The phase 2 is for the soil structure interactions. Phase 3 is for the hydrodynamics under the motions, and the phase 4 is for the hydrodynamic challenges. And the OC6 project spanned from 2019 to 2023. Actually, it officially ended in early 2024 for the CFD part of the phase 4. And the OC6 implements a 3-way validation processes that compares both the engineering level modeling tools and high fidelity tools such as CFD to the measurement data. And the CONVERGE CFD has been used for the works in the OC3 and the OC4 by our partners. Let's take a look at the OC6 phase 3 project first. The purpose of the phase 3 is to aerodynamic loading on a wind turbine rotor undergoing some prescribed large motions. The wind turbine studied here is the DTO 10 megawatt reference wind turbine. This is a conceptual turbine, so it's not actually being manufactured. to study this problem, people build a scaled model. It's with a ratio of 1/75 and tested this scaled model inside the wind tunnel at the Polytech Milano, Italy. And as shown in this photograph, you can see that there are two different designs of these experiments with different supporting structures. And therefore, they have different stages of the experiments. And in the upper table, you can find all those details about the full-scale turbine as well as the details of the scaled model in the experiments. And the experiments in the OC6 phase 3 problem actually tries to make the comparisons of the loads for the steady and the unsteady wind conditions. The steady condition means that we have some given wind speed, but the platform is fixed. For the unsteady condition, the wind condition is the same, but the wind turbine itself is forced to move under some harmonic motions controlled by the mechanism shown here. And in total, there were 28 participants in the OC6 phase 3 project. They were using different numerical models, including different types of the engineering models, such as BEM, DBM, GDW, FWW, and some of the participants choose to use the high fidelity methods, such as CFD, for the work here. One of those CFD participants was the Professor Alessandro Bianchini's research group at the University of Florence, who choose to use CONVERGE CFD as their main CFD tool for the work here. And in these slides, what I'm showing are the detailed descriptions of the load cases that have been studied in the phase 3 project. As I said earlier, we consider both the steady wind condition and unsteady conditions. For the unsteady conditions, we consider both the surge motion and the pitch motion. And the different types of the surge and pitch motions are studied as well. And in the following talk, we are going to show some selected cases as a demonstration. We are going to show the steady wind case, load case 1.1, and the load case 2.5 for the surge motion, and the load case 3.5 for the pitch motion. And let me give you a very brief introduction of the methodology, CFD methodology used by the Unify team. So basically, they try to use a method called actual line model for the aerodynamic modeling of the blades. The actual line model is a very popular hybrid model that combines the mid-fidelity aerodynamic methods for the blades and the high-fidelity CFD flow field solver. So basically what it does is that instead of resolving the geometries of the blades, the actual line treats them as the moving actual lines, the visual lines, and at each point or each section of this actual line, we can calculate the local flow conditions from the CFD simulation, and by given the configurations of the blades, we can obtain the local angle of attack. Then from the angle of attack, we can find the corresponding lift and drag coefficients from the turbulated data. And once those lift and drag coefficients have been obtained, we can calculate the overall the local aerodynamic forces and feedback those aerodynamic forces back to the CFD solver. Therefore, the CFD solver can feel the aerodynamic effects from the blades. And this coupling has been done at every time step, and this is a two-way coupling approach. By adopting this method, as you can see that we can simulate the blades in a very numerically efficient way without sacrificing too much of the accuracy. Meanwhile, we can obtain the benefits brought by the CFD, which gives you the very detailed flow conditions. And besides the actual line model used on the blades, the Unify team choose to resolve the geometries of the nose and the nacelle for the for the wind turbine. And for the turbulence model, they use the K omega RNG turbulence model in their simulations. And in terms of the mesh resolutions, it varies at different locations of the domain. For example, the resolution in the near wake region is about 3 centimeters. The near wake is defined as the less than 1 diameter of the rotor after the wind turbine. And the resolution is a little bit coarser in the far wake region, which is 6 centimeters. And they also activate the adaptive mesh refinement for the velocity, trying to capturing the detailed flow structures, especially those vortex structures generated in the wake region. Let's take a look at the results of the load case 1.1 first. This is the steady condition. And as you can see that I show 3 different results here, which includes 2 results representing the overall loading effects, such as the aerodynamic rotor thrust and the averaged wake deficit within the rotor regions. In those results, I plot the results from the different numerical models are represented as a color bars, in which the converged result is this purple bar and the purple bar here. And we also included the 2 experimental results here for the thrust and 1 experimental results here for the deficit. As you can see, in general, all the numerical results give a satisfactory or reasonable match to the experiment data, and they are pretty comparable with each other. That is not surprising. And but if you go to the more detailed flow structure results, such as the average blade tip vortex trajectory measured inside the PIV plane, and as you can see that compared with the high fidelity CFD results, which are the solid lines, the mid fidelity results seems to be a little bit away, showing a little bit larger discrepancies compared to the experimental data. And the CFD in general has a much better comparison to the experimental data, especially for the converge. As you can see, we agreed pretty well with the measure data. This seems to indicate that the engineering models did a pretty decent job to predict the overall loading performance. But in order to but if you want to look at more detailed flow structures, such as the vortex structures in the wakes, then the high fidelity CFD is more preferred. And we know that the dynamics of the vortex in the wake has a significant impact to the efficiency of the downstream wind turbines. So this is critical to have a successful assessment of the efficiency of a wind farm. And next, let's take a look at the results of the load case 2.5. This is the unsteady surge motion case. The surge motion is defined as the translation motion along the wind direction, as shown in this diagram. It's a little bit, well, it's actually quite exaggerated. Actually, the amount of the motion is pretty small. It's like 0.035 meters with a hertz, 1 hertz frequency. And we plot the aerodynamic rotor thrust averaged in phases from different numerical models, as well as from the 2 experiments. The converged result is shown as the purple line here. As you can see, because of the motions, the results, the rotor thrust has the maximum value when the rotor is at the center of this motion, where the velocity is the highest, and the thrust are the minimum at the 2 extremes of the motion at 90 degree and oh, I'm sorry, I made a mistake here. Actually, the minimum is also at the 0 degree and 360, which is also at the center, but it's with a different motion type. And but in general, as you can see, the converged results matches pretty well with the experimental data, and it's located in between the 2 experimental results, and it's well inside the range of all the numerical results. And next, let's take a look at the load case 3.5 unsteady pitch motion, and the motion type is the demonstrated in this animation with some exaggeration. The magnitude is 1.4 degree with frequency 1 hertz again. In terms of the results, we show the aerodynamic rotor thrust and aerodynamic rotor torque. Unfortunately, we don't have the experimental data to be compared with the numerical results, but at least as you can see that the converged results locates pretty well in the middle of the ranges of all the numerical results. And also those two performance shows the variations according to the different rotating angles. And the phase 3 was ended about 1 year ago, and it has achieved some very successful, very encouraging success, but there are still a lot of unanswered questions, especially for the wake structures and the turbulence effects and the interactions between different wakes. Those important factors were not included in the OC6 scope. And therefore, there are several projects that has been proposed. One of them is the Neptuno project. This is an EU-supported project trying to look at the wake properties and the wake interactions of multiple floating turbines. The experiment will still be performed inside the Polytech Milano's wind tunnel based on the same wind turbine, and Unifi again will be one of those main participants for the numerical models. This time they are trying to use CONVERGE CFD for the LES simulations rather than the RAN simulations, because here they try to capture in more detailed flow structures in the wake physics. And such as showing in those figure and animations, as you can see, by using LES, CONVERGE can capturing all those very detailed flow structures. And this is a very important and ambitious project, and we are really looking forward to its future progress. And after talking about the phase 3, let's shift gear a little bit to the phase 4 project. The phase 3 project was mainly focused on the aerodynamic part of the rotor, and the phase 4 project was trying to focus more on the hydrodynamic part of the supporting system. And the goal is to validate the numerical models for a novel TerraSpar platform showing in this figure. As you can see, the platform has two parts. One is this upper lighter hull part, and the other is the lower heavier keel part. And this structure was manufactured, but it's with a very big scale, as you can see compared to this truck here. So in order to study the dynamics, a scaled model with a ratio of the 1 to 43 based on the Froude number scaling was carried out at the water tank of the University of Maine. And the lower two photos showing the measurement facility. And unlike the OC6 phase 3 project, the phase 4 project divided the participants into two consortium. One consortium was mainly focused on the engineering models, and there were 16 participants. And the other consortium was mainly for the CFD simulations, and there were only 3 participants. So it indicates to you that how difficult to run the CFD for this type of the simulations. And Convergent Science this time directly participate into the CFD consortium teamed with Professor David Schmidt's research group at the University of Massachusetts. And we worked together to build the models, to run the cases, and discuss the results, and wrote the papers. And let's take a look at the structures of those platform first. As I said earlier, this platform includes two main parts. One is the hull and the other is for the keel. In the reality, these two parts are connected by 6 Q lines or the taut cables. Those lines actually are flexible, but it's actually quite rigid. It allows some relative motion between the hull and keel, but it is found that relative motion is not big enough. Therefore, in the CFD simulations, as a grade for all the members of the CFD consortium, we decide to treat the whole system as one rigid body, and therefore we can neglect all those the keel lines. This is mainly for the simplicity of the modeling, but it may also contribute a little bit to the discrepancies from the CFD results to the measurements. And in terms of the mooring system, this platform has been connected by 3 mooring lines. The mooring line 1 and 2 and 3 on the 2 sides of the structure, and the mooring line 2 is along the wave and the wind directions. The mooring cables are connected to the hull part on one end, and on the other end they are fixed on the seabed. And in the figure here, it also shows two yaw bradles. Actually, those bradles were not included in the CFD simulations because we only simulate some selected conditions where those two lines were not included even in the experiments. And one challenge here for the mooring cables is that the mooring cables does not have a uniform property. It actually consists of 2 sections. It was a heavier lower section and upper lighter section with different properties. Therefore, the mooring cable has to have the capability to deal with the variable properties of the mooring cables. And another challenge or uncertainty in the experiments at CFD is this umbilical cable. This umbilical cable was used in the experiment to transfer the data during the measurements. It turned out that this cable actually has some substantial impact to the dynamics of the platform. Therefore, in the CFD, we had to include this cable. However, we were not sure about the exact properties of the cable. Therefore, we adopt a strategy to do some try and error test, trying to make the simulation as close as possible to the experiments. But nonetheless, there might be some differences in the cable properties, the umbilical cable properties in the CFD and the experiments, which also contributed to some discrepancies in the 2 sets of the studies. And in terms of the CFD methodology here, instead of using the simulating the scaled model, we prefer to simulate the full-scale model with the wall-modeled LES approach. And the multi-phase flow was modeled by using the VOF method with the H-rig scheme. And to generate the waves, we are using the theoretic wave generators at the inlet. And to absorb or damp out the numerical wave reflections, we added relaxation zones at both the inlet and outlet. And in terms of the mooring cables, we adopted a dynamic mooring cable approach based on the lambda mass model, as shown in this diagram. This model also includes the interactions between the seabed and the mooring cables. For the cases where the aerodynamic impact is included, we adopted the line model that I described earlier in the phase 3 project for the blade simulations. And the computational domain we used is this box domain, which is big enough to include 3 wavelengths. And we generate the theoretic wave at the inflow by following either the Stokes wave theory or the irregular wave spectrums, depending on the given wave conditions. And we also add the relaxation zones with the length of the one wavelength at both the inflow and outflow to reduce the numerical wave reflections. And in terms of the mesh, we are using the Cartesian mesh with a cut cell approach to deal with the structures. And the resolution, again, varies at a different part of the domain. And basically, we have some finer resolution to across the whole wave height to better capturing the wave dynamics. And we have some relative fine resolution on the upper part of the water to capture the wave velocity and the pressure. And we have fine resolution on the structures. And we also activate the adaptive mesh refinements to give some further resolution following the free surface evolution. And for the cases where the actual line model was used, we have the AMR to capturing those virtual blades better. And the first test we performed are the equilibrium and the free decay cases. And the equilibrium study is trying to find the actual hydrostatic locations of the platform, based on which we can perform the free decay test. And here, what I show is the comparison between the CONVERGE results and the experiment results in terms of the final offsets in the equilibrium tests. So in the equilibrium test, we prescribe the initial location and let the CFD go until the simulation gets to the steady equilibrium, and then we measure the offsets. And as you can see that the CONVERGE CFD results match pretty well to the experimental data. Note that all the data showing here are in the full scale. So the difference you observe here actually are very small. And after obtaining the equilibrium state, then we simulate 3 different free decay cases. The free decay means that from the equilibrium, we intentionally gave some initial offsets to the geometry, to the floater in the given directions. Then we measure the recovering process and until it reaches to the equilibrium again. And the 3 cases we look at here are the surge decay, wave decay, and pitch decay with the initial offsets given as shown here. And the animation here is the process of the wave decay simulation. And now let's take a look at the results of the free decay cases. As you can see, we plot the time history of the surge, wave, and pitch motions from the CFD results, as well as some mid-fidelity simulation results and the experimental results. The experimental results are shown as the dashed line. And as you can see that in general, all the modeling results, no matter it's CFD or mid-fidelity results, they captured pretty well in terms of the damping frequency or the damping period, as shown in those bars here. But in terms of the damping ratio, as shown here, we show the surge damping ratio, wave damping ratio, and the pitch damping ratio. We observe that the modeling results has lower damping ratio compared to the experiment. So which means the modeling, for example, the CFD damps less compared to the experiments. The reason is still uncertain, but it can be contributed by different factors, such as the uncertainties about the umbilical cable, or the interactions of the seabed, the friction on the seabed. Either the friction of the seabed was not simulated by some of the CFD, or it was simulated with different parameters. And also, at least in CONVERGE, we did not include the aerodynamic drag from the turbines in this study. Therefore, it also underestimated the dampings. But in general, as you can see, the modeling results seems to predict the similar trends, and they are more comparable with each other. And in some of the results, CONVERGE CFD seems to have a better match to the experiment. And after the free decay cases, we take a look at the aerodynamic studies for this floating offshore wind turbine. And basically, what we have done here is we have some calm water, then we impose some steady wind above the water, And then we consider two conditions here. One is with the floating condition, the floating turbine, and the other is with the fixed turbine. Then we measure, for example, the thrust forces for both the floating cases and the steady case, and also the motions and the mooring cable forces in the floating cases. The wind speed we look at here is about 9 meters per second at the half height of the turbine. And in our simulations, the tower and the structure are directly resolved by the CFD, and we will using the actual design model for the blades, as I mentioned earlier. And also, as I said, we use the adaptive mesh refinement to further increase the resolution to 2 meter in the rotor region. And this slide shows the comparisons of the CFD results versus the experimental data for those measurement metrics. Here is the aerodynamic rotor thrust for both the floating case and the fixed case. As you can see that the CONVERGE results had a very good match to the experimental data, which is this dashed line here. And we also compare the relative hull pitch angle in the floating case between the CFD results to the experimental data. Again, the agreement is reasonable. Then we compare the field lead tensions at the three cables. As you can see that the tension at cable 1 and cable 3 has have very, very good match to the experiment. Those two cables are on the two sides of the floater. But at the cable 2, which is along with the wind direction, as you can see, both the CFD results, well, the two bars means two different CFD results, and the blue bar is from the CONVERGE. Both of them underestimate the tension at the cable line number 2. This is because, for some reason, in the experiment, the cable or the floater has some initial surge offset at the resting conditions before applying the wind, which means it has some preloaded tension to the cable number 2. This phenomenon was not observed in all the CFD results, and the reason is still unknown to us. I mean, the reason for the pre-surge in the experiment is still unknown to us. And after that, let's take a look at two wave conditions. One is for the regular wave, which means the wave has only one wave period with one wave height. And the wave parameters are given here. The wave height is about 8 meters and the period is about 12 seconds, all in the full scale measurements. And this animation shows how the response of the floater look like under these wave conditions. And as you can see, we also show the mooring cables as well as the umbilical line here. And in terms of the results, we plot the comparisons between the CONVERGE CFD versus the experiment in terms of the response amplitude operator roles for all the surge, wave, and the pitch motion modes. The roles are the ratios of the response amplitude, for example, surge, wave, or pitch, at the wave frequency divided by the incident wave amplitude. This is a commonly used parameter for the hydrodynamic analysis. So as you can see, the CONVERGE results have a reasonable match to the experimental data. And next, we simulate the irregular wave cases. This is one of the most challenging cases that we simulate in the whole OC6 project. Unlike the regular waves, the irregular waves consist of a bunch of different types of the waves with different wave heights, wave periods. So instead of looking at one wave, you have to consider a range of the spectrum for the waves. The spectrum we adopted here is a modified John-Swab spectrum with the key parameters defined as the significant wave height, the dominant wave period, and the peak enhancement factors. By given those parameters, we can determine the wave spectrums, and we then convert the wave spectrum into the wave heights and the wave periods introduced at the inflow. Before running the hydrodynamic studies, we run the wave only cases first, trying to see if the CONVERGE CFD can capturing this complex irregular wave in a decent way. And this is what we obtained. We run the wave only cases for 3 hours, then we obtain the time series data. We convert the time data into the spectrum domain, and we compare the spectrum of the wave elevations. And as you can see, the CFD results, which is the blue curve, has a very good match to the experiment, which demonstrates that CONVERGE is quite powerful to simulate these irregular waves. And after running these wave only cases, then we simulate the same wave for the hydrodynamic conditions with the inclusion of the floater for 1 hour in the physical time. And as you can see that we obtain the results, the moving results for both the surge, wave, and the pitch motions, and then we convert the time series data into the PSD, the power spectrum density, and we compare the CFD results to the experiments. As you can see, the CONVERGE CFD is able to capturing the spectrum peaks at both the natural frequency and also at the wave frequency in all the 3 different modes of the motions. Okay, I think I will stop talking about the OC6 for now. I hope I have already shown you that CONVERGE has achieved some great success in the OC6 projects, and we are really happy about what we have done. And right now we are moving forward to the OC7 project, that is the undergoing OC projects. And this time we are collaborating with University of Massachusetts and the IFPM, and as a team. Right now we just finished the phase 1 project of the OC7. In that phase, we look at the 3.5D and 3D forced motions and the 3D floaters for the equilibrium, free decay, and regular wave conditions. From those photos, you can have a glimpse of what kind of problems, what kind of floaters that we're looking at in this OC7 phase 1 project. And we're really exciting about this collaboration and for the future works. And if you are also interested, please keep in tune, and we will be happy to share you the exciting stories about our work in the OC7. And at last, I want to show you all those reference papers about the OC6 project, from which you can find the very organized results and the case descriptions and the methodologies from the different participants. And most of the works are open access, so it's easy to download and read. If you're interested, please go to those papers for more details.